first of all, I have to state that all the planets are in rotation. And they rotate, of course, around their own axis. First of all, of course, our Earth. Everybody knows that it's rotates with a period of 1 day, 24 hours. It's slightly changed. It's interesting to note that for the Earth, this rotational speed is decreasing with the time, because there is very sufficient influence of the tides from the moon and so on. So usually the length of day become longer, and so speed of rotation, the angular speed, usually we use angular speed of rotation, like here, so this angular rotational rate. So angular rotational vector, which is defined like this way. So it's for the Earth, it becomes smaller and smaller, and for consequently period of rotation becomes longer. So our days are progressively longer and longer. It's interesting if we model it, consider it back in the past. So it was, I don't remember exact figure, but few times more faster. Earth was rotating, and Moon was much more close to the Earth. So it will be very big tide, and not like now, which just maybe. So it was a very big influence. The similar situation is on another planet. All of these planets are also rotating rather fastly. And maybe the champion in this sense is Jupiter. It's the largest king of the planets in our solar system. And it's rotating tremendously fast, about 10 hours. Such a massive object rotates with such a fast speed. But if we consider, for example, Venus, the Venus is much more close to the Sun. Not much, but on some sense. And it's rotated. There is the gravitational tide which linked it to the Sun, so it's rotated about 100 days, 200 with something days. So its period of rotation is in 2 orders of magnitude larger. So consequently, the angular rotational rate is 2 orders of magnitude, 100 times more faster than in the Earth. More exactly, even 200 times. And the similar situation is with the Mercury, because it's very close to the Sun, and so the Sun influences it to look on the Sun only from one side, like Venus did as well. And it's rotated about, I don't remember exact figure, but without about 100 with something days. It's the rotational rate of the Mercury. If we consider Mars, this Mars is, also has a period very close to the Earth, just slightly different. So we have 24, they have 23. And it's interesting phenomena that some people, if we isolate them from everything, they put more often their period of life, synchronize it with Mars time, Mars period, not with Earth. It's interesting. So maybe in some sense we are all Martian. Cool. Okay, let me proceed now after this short introduction. And also, all the planets, as I state, rotate around their own axis. Therefore, the most convenient system of describing their interior is a coordinate system rotating together with the planets. Let us consider in detail the simplest and at the same time quite realistic situation. When such a non-inertial, it should be stressed, because if we are going to the rotating system, it becomes not inertial, it's non-inertial system, and it's a very important point. We should understand it always. Its non-inertial coordinate system rotates with an angular velocity of rotation omega. We made it with angular rotational omega. Oh, I keep losing. Okay. Oh, yeah, mouse. angular velocity omega. So we suppose that it's constant in magnitude and direction. I just told you that virtually this, of course, changed somehow, not only in the value but in the direction as well. So there is maybe the precaution of the code, so it may change the direction. It's rotate like that. So of course it's changed, but to the very high accuracy on the period of some even million, some 100 million years, we can suppose that it's constant with very good accuracy, because the characteristic change of the full lattice system is a billion years. So characteristic time for the full change of the angular rotational rate, sufficient change of the angular rotational rate is about the billion years. So of course on the period which we investigate, sometimes of course when we consider it, especially Earth, we're going up to some million years and even 100 million years, and still at this period we can keep approximation that the angular rotational speed is more or less constant. So it's a very good approximation. So why not to start from it? So the polar axis of the corresponding spherical coordinate system, r theta and phi. So we're using standard spherical coordinate system like that, and is directed strong. So it's directed along the vector of the constant angular velocity of rotation, or maybe formally we can write it like it was written here, So we can. It's interesting to note. Sorry. I'm suggesting here for you to use, if we write down the angular rotational rate, this is the vector, it has a value and direction, and I'm suggesting that we separate magnitude, and in fact this magnitude can be multiplied by the unit vector, and it's quite convenient on my point of view to use just gradient from the corresponding value of the variables, the spherical variables. If we consider that it's directed along the axis of rotation, then it will be in Cartesian coordinate, z coordinate. And if we see this in spherical coordinate, it will be r cosine theta in the spherical coordinate, this z component. I just stress that this is unit vector in z. And from my point of view, not only my point of view, it's quite convenient to use this notation from which we can directly identify how it works. Or maybe we can just replace it like that. Omega gradient z, where z is the Cartesian coordinate. Okay, it's one better, yeah? Yeah, but you say that it's this better?
Yes, this is better.
Yeah, okay. So the polar axis of a corresponding spherical coordinate system, r theta phi, is directed along the vector of this constant angular velocity of rotation, or other words, we just wrote this, what I wrote. We will use this spherical coordinate system and unit vectors. I stress about the unit vector. It's quite convenient to use this unit vector. Let me stress this point, that we can represent the unit vector quite naturally via the corresponding gradient of the. Of course, we can do it not only with this, no, not only with this z value of the Cartesian coordinate, but with any value. So we can very easily to find the unit vectors in different coordinate systems. So this is just a way as I showed. Okay. So we will use, but in general, we will use this spherical coordinate system and unit vector, which are the vector of the gradient of the coordinate multiplied by the corresponding Lamé coefficient. So that's my suggestion to use this gradient stuff to define the unit vector. It also could help for us to identify some Lamé coefficients. Moreover, unlike the Cartesian system with Lamé coefficient equal to 1 everywhere, the direction of the unit vector in the spherical coordinate system depends on the coordinates of the point under consideration due to the fact that the Lamé coefficient of angular coordinate is spent. Let's now see on the coordinate system here. Yes. So Lamé coefficient for angular coordinates depend on the radius and the polar angle theta measured from the polar axis, as it's shown on this picture. The unit vector are all mutually orthogonal in the coordinate system under consideration. In the spherical coordinate system, so see this figure, the angle theta is the azimuthal angle, and the unit vector corresponding to it complements the unit vector to a right-hand side system, complete to the right-hand side system, and its direction is determined from the cross product. Actually, for example, if we determine the theta coordinate system unit vector, so it's almost it's virtually correspond to the cross product which is written here, and this cross product is if we want to identify the unit vector in the phi direction, in azimuthal direction actually, we can replace it like that using the similar stuff like here. And it's actually equal by the to the cross product of the unit vector in r direction multiplied it by unit vector in the theta direction, which we can represent like that. So in some sense, it's convenient system to go from one unit vector to another unit vector and to represent them in such a simple, relatively simple style. So in the direction of movement of the right-hand side screw, which rotates from the vector gradient r to the vector gradient theta. So we just use right-hand side. So we from gradient r we rotate to the gradient theta. Here the gradient r and here the gradient theta. So we rotate this direction, and then this phi vector is going this direction, just around the axis of rotation. So everything is right. So we just used right-hand side screw to identify the direction, how it works. So please pay attention to this coordinate system, and this is system not only make us to understand us how this unit vector stuff is working, but also it's just for the planetary interior. You see the inner core with the radius of Ri, and there is the outer core, which is the outer core which is liquid in the liquid core. We contain mainly iron, and it has Ro radius, which we'll use further in this fashion. why we chose for inequal I, index I, it's because the inequal just started from the inequal. And this we use the O because it's outer. So this is for the outer core. But nevertheless, it seems quite convenient. Everybody is used to this. So let's proceed further. And in the internal coordinate system considered here, is considered above, the absolute velocity u with vector is expressed through the translation rotation of the coordinate system in figure 4, which I previously showed you. This figure 4 and this picture, and the relative velocity. Here after simply velocity. So this simply velocity we will consider hereafter. And it's translated by the very simple formula. So we take in the total in inertial coordinate system, total in inertial coordinate system velocity u. It's actually have a two component. First component is related to the angular rotation with the constant speed, and everywhere it's could be described by the simple relation. We are making cross product of the vector of angular velocity with the vector of spherical radius, and then we add our relative velocity, which is in this coordinate system. And this relative velocity, we usually, quite usual question, we just use capital V with vector sign, so it's the vertical velocity. So now we are, our goal is to understand how this system transfer to the different equation, to another different equation in the rotating system. So we substitute 14. This is the 14 formula. Oh, sorry, 16. 13. It's formula 13. Somebody regard it as unhappy number. So I made a break on it. And substituting this 13, inside the chapter, I will not name the number of the chapter. I will just send the number of the inside this chapter. So we're substituting 13 into equation 12, previous equation, which was shown to you before this one. Equation 12. It's not on this slide, but nevertheless, just believe that if we substitute it in 12, then we obtain eventually, after some transformation, it's important to note that we obtain after some transformation, we obtain this equation, dv by dt plus v gradient v plus, and a very important term from the Navier-Stokes equation, which we derived in the previous chapter. So we see that we will have this system, and it has only one addition, actually, literally. This addition is the angular velocity with two coefficients multiplied it in cross product with velocity. And also there is a gradient P, but it should be noted that it's not capital P, which was used in the Navier-Stokes system. It's slightly another P. And there is still remain the other forces which we can take into account. And the difference is that it's now divided by rho. And there is in the hydrodynamic system of four-scaled equation, normalized effective pressure hereafter simple pressure is used. So this small p letter is for the reduced simple pressure or effective pressure. There is different name for that, but maybe normalized the effective pressure or all this together. But later we just call it just pressure. And this is formula is 114. 114. So, and this is important to know that this normalized pressure P is equal capital P. So this is thermodynamic pressure. It's not normalized, but initial pressure divided by density, which we suppose constant here under this approximation. And there is centrifugal force contribution, which scalar part is look like that, very simple. So we have omega value multiplied it by actually z coordinate, but in spherical sense it will be r sine theta, and all this is squared and simply divided by 2. So 115. Okay. So actually the system 14, this system 14 is completely closed with the no slip boundary condition 11, which we will discuss in more detail in the next chapter. So there is one task which has some sort of, so we now have some introduction, have we reached this simple formula to write down the, I just should name that this is the Coriolis storm. There is only one addition actually, formally only one addition, there is a Coriolis storm. There is also some transformation of the thermodynamic pressure to the normalized or effective pressure, whatever you like, which is include not only divided by the density, but also include centrifugal gradient, which is coming in this equation like that. So the task actually, which I will show you in some detail, the first task which appear in this course, and so I will show you how it works, that you understand, and then easily repeat after that. So the first task is formulated like that. Proof based on definition 0 and 1. It's related to my second lecture actually. And in this definition, we just define the Navier-Stokes equation. That during the solid, proof, it's necessary to prove that during the solid body rotation of the medium, it is shown in figure 2. Above, there are no stress at all. The problem is that if we started our course of the lectures with viscosity, and we also consider it about some stress terms. And this stress term, so of course it seems obviously if we have the solid body rotation, there is no any stress. It should be. But all mathematical life to prove everything, they didn't believe just in words that if we consider the solid body rotation, so there is no stress. Why not to calculate that? It's not so easy method, but maybe some exercises. So let's start to try to prove. And to prove this, based on definition, for proof, we will select a vector of angular rotation, velocity of rotation, fixed for the entire medium with constant Cartesian coordinate. So, and formally describe the velocity v of a point in the medium with a radial vector r. So formally, okay, maybe I'll remove that stuff. So actually, as we already defined this velocity, so we are suppose that everything is solid body rotation. What does it mean? That velocity, our relative velocity, is solid body rotation. So we first things we remove related velocity. We just suppose that all the real relative velocity is described by this term, which is responsible for the angular rotational rate and corresponding solid body rotation. And of course, we suppose that this omega stuff has fixed coordinate. So let's just expand this fixed coordinate in Cartesian system. So it becomes x component of omega multiplied it by unit vector in x direction. I'm using this more simple notation because from my point of view, it's more easier way to understand its physical value. So we just using the cross product. Oh, sorry, not cross product, but gradient. No, so it's correct. Sorry, gradient of x. Then in the similar fashion, we expand the next coordinate of the angular velocity, so with gradient of x, y, and then plus omega z with gradient of z, and then it should be multiplied on the radius vector, and Cartesian coordinate system, it represents like this value. And so, of course, there is a we should multiply everything, and eventually we are getting that the first term where we have the similar product of the, for example, with gradient x and here with gradient x. Of course, by definition, if we take the cross section of these values, it should be 0. So we just start from the everything which is written here, and the first term which is responsible for this multiplied it to this is of course 0. Then the next term is omega x y when in accordance with this rule. So it's this cross product of the corresponding term will give us gradient z. Then again, using this right hand side screw, we get in the next term, which is again go with near the omega x value. Gradient y. So it's come. Then again the next minus term. Now we at the moment we just multiplied it by this term. Now we start multiply with this term of all these values which are in these brackets. So then we have y, omega y term multiplied it by x and gradient z. And here we have again 0 because we proceeded to this value which multiplied it by this. And if we have the same vector multiplied it in cross product, it's of course 0. Then we have next term which comes with plus. So now we zero x, and there are remaining z terms which correspond to this term multiplied by all the stuff which is appear here. It's plus omega z x gradient y. Then there is following term which will come with minus sign omega z y gradient x, and eventually we have multiplication of these z terms. So it's of course 0. So there is a 0. So actually we expanded the vector product of the angular rotational rate over the radius. And now to make the complete understanding how this stress works, we should represent the nabla term. Of course, we're using quite standard representation that the nabla term is actually equal, even by definition, d by dx. It's a x coordinate system in Cartesian coordinates, then d by dy and d by dz. It's quite notional, quite usual. So it's against coordinate unit vector, or like that. So, of course, people sometimes use another notation. Sometimes they use like that. Sometimes they use like that. There are a lot of notation for the unit vectors. And there is even like such a funny notation like R1, Z. Somebody used that. So there are very many notation for the unit vector. But from my point of view, this one is the most suitable because it's directly outlined what is the physics and how this thing is working. Because you just take the gradient of corresponding value, and it's work in any coordinate system. You can take gradient from the corresponding spherical coordinate, you get the unit vector, and so on. Okay. So we will now finally verify that all possible local shear stress for solid body rotation are equal to 0 by differentiation the expression for the velocity obtained above accordingly. So there is some space we just write down here. So if we take the component of the stress, which of course contains some plane, so if we take the y plane for the stress, so here there is x and y, so there is a plane. Of course, we are taking some local position of this plane, but nevertheless this plane is against x and y. And there is a general rule which I previously showed to you, that we, to define this stress component, we use the sort of the cross. Of course, the first we have the dynamical coefficient of the viscosity, and then we just, so if this is xy, then we start with x component of the velocity, which is, we have the partial derivatives on the y. So x, if we use the x here we have y. So it's the y. And the next component of the stress is correspondingly just cross. Y comes here, x comes here. So quite simple. So we have dv y on dx. So such a cross. Then we can outline the component of the corresponding angular rotational vector, which we use here. So from this velocity, we make this inequality. We just collect corresponding part of all this. For example, near the unit vector z, we collect this, collect this, collect. There is 0. So just to, for example, for y, we collect near the unit vector in direction of y. We collect this, and again 0, and so on. So eventually we have the relation that we use the angular rotation, again coefficient of viscosity, and then we, as I already told, we make such groups, and these groups, in terms of the derivatives, then can be represented as following. So we should take the derivatives in respect to y, of course from the x component, like we saw here. And this x component has two components, of course, because one is 0, as I already told, but there is another two component remains, and it has such a component like minus omega z y. you see that it's precisely we consider now x component. So first time it's appear here. So we take this z, this z comes from here. And the next time it's appear here, you see that we take from y from here. And of course this story repeat everything we do in the similar fashion. Okay, let me. Okay, I'll start from the very beginning because it's necessary to do so. So for another component, this component, y component, we again outline it from here. And it's look like it's interesting that we always have type of the cross. There is z component here and z coordinate here. There is a x coordinate here. There is a component x here. So there is such a rule which make this sort of the cross. And here we, okay, taking dx. And this we close the bracket. And then the next component of the stress. Of course, we just make different combination of x and y and z planes. And there are 3 different choices. And the first choice is just started with x, y. Then the next choice we can use is stress component which has yz. And it's okay, of course, obviously working the same way, similar way, not the same, of course, exactly, but the similar way that we have dv y by dz plus dv z by the y which is equal, again, we just expand here. Oh, sorry. Yes, and again, we collect in the terms which are correspond, for example, here the y component of the velocity, and so it's look like with знак minus, with sign minus. Again, we see this cross rule divided by the z, and then we have a plus, and the last term in this stress, d omega x y d y minus x and let's just write down the last one. I will not comment, just write down. So we have zx component Actually, it's all by definition again, of course. And here we again has z component and x component of the velocity. Oh, here extra. Okay. Okay, we're finishing. Dx. And eventually the last term, not the very last, but at the moment, minus dx. Oh, sorry, yeah, seems I miss. Oh, sorry, I just repeat that one. Okay, seems I didn't write it down correctly. So everything is written here, and surprisingly, bingo, if we just take these derivatives. So in total, all the big things begin from this one, then it becomes 0. You can just derive it yourself, and then this one also becomes 0, and every stuff becomes 0. This 0, this 0, and this 0, of course. So actually, it's proved from the formal way that there is no stress. Very simple proof. So, okay. 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 Do we have the time or do to? Hmm? Okay, yeah. Thank you. Oh, maybe right, yeah? Oh, thank you. Okay. Okay, I don't know. Could we finish just for the break because without our spend, or maybe less. Yeah. It's possible to put spherical coordinates the same. But of course, the Cartesian is more simple. In spherical, there is some more.
But the procedure is same.
And especially using this advance, which I'm suggesting to use not simply a unit vector which will represent the Lamé coefficient, but you just take the gradient of the corresponding vector, and it's more easier than this Lamé coefficient has some natural.
Here we have the angular space between two spheres. That is the case also.
Yeah.
Stresses.
Yeah, you also can, in any case, you can calculate. Of course, I showed the simplest example, when there is solid body rotation. But of course, we can do any. It will be more complicated, of course. Even this is not so easy. Okay, maybe there is a question. There is one more task on this subject, but I'm afraid that we don't have enough time for it. Maybe we shift it on the next lecture.
Okay, next lecture we will do that task. Okay.
Okay, thank you. Yeah. To finish the second task in this chapter, and this second task is formulated. Having carried out the necessary identical transformation, proves that after substituting 13, after substituting 13, the formula 13, this formula which I show you by the mouse, which includes the solid body rotation and relative speed, that if we substitute it to the initial Navier-Stokes equation, it's necessary to prove that after substituting this 13 into equation 12, it's not written here in the previous slide. Okay, this 12 equation is actually Navier-Stokes equation. I will not repeat it now. So we obtain equation 14 and 15. 14 and 15, this equation, after substituting this in the original Navier-Stokes equation without rotation in inertial system. So eventually we are getting a non-inertial system, this equation and this. But we omit the step, how we put it there and what the transformation happens to arrive to this formula, and to this formula as well, of course. To make this manifestation in the non-inertial coordinate system. So okay, let's start, and let's dissolve some number in this formula, and we start from this substitution. I just remind you that in this formula we have, we should substitute 13, which is on this slide, to the initial Navier-Stokes equation, which we discussed in the previous to the previous lecture. So I will not collect it here, but just believe me that I will try to substitute 13 right to the vector equation 12. And so the first term is actually partial derivatives of the full velocity. This full velocity is contains rigid body rotational term and relative velocity. So this velocity contains all the stuff and its partial derivatives. So we just replaced u, small u, with this combination of rigid body rotation and relative velocity. Then we should do exactly the same in other places. Okay, sorry. I was a bit hurry. So the first is this Rossby term, u grad u, and when we replace u by this value of rigid body rotation, and we put it in brackets just to distinguish, then it's multiplied by nabla operator scalarly. Then we have again this number operator. We just have velocity again multiplied it by nabla. We just expand this relation to make it clear, and here the bracket is closed, and all this stuff is acting on this, the same stuff, u, it's acting on u, and in this case, in this expansion, it's acting on solid body rotation multiplied by r plus v. And eventually everything is equal. We just a little bit transform this form just to keep the velocity term in one place and all other velocity and classical sort of velocity term with in one place, and which is related to viscosity and other stuff, we change it to the another place. So we are using kinematic viscosity here just to make things simpler. Then we have a Laplacian, and this Laplacian is acting now on this combined angular velocity and radius vector and relative velocity, of course. And finally, we have this generally accepted other force. Also, there is gradient of thermodynamical pressure, and here we finish up with density. And this is formula 116. You can find it in the text. Rani is the Rani is not here. Huh? Okay. So I just asking, maybe you know all this text with all this detailed text are accessible. Yeah, we have a text on our Spark project page where there's written all this stuff. Is it accessible? I don't know what is the policy. Maybe it's accessible to the student, maybe not. I'm just wondering. But at least there is some place where all this stuff is stored. But maybe student will have access after exam. I don't know. Okay, I just asked. Later we will ask Rani, Professor Rani. Yeah. Here. Yes. It's short. Here. Thank you. direction. Here is plus 2, because here we have plus force and the negative sign is identity. So some correction and just forgot it. So an initial Cartesian coordinate system with axis like that, initial coordinate system with all axis and coordinates which vector form on the y, directed along the constant angular velocity vector. Angular velocity vector in z direction, of course, and this we use it, simplifies this stuff a lot. So, and the constant angular velocity vector, the expression of translational rotation included in 16 is simply as follows. So, if we just for simplicity direct it in the axis of rotation, this angular rotational rate, just to simplify all the stuff a little bit, then this term, this very important term, omega cross r, could be expanded. You see that the omega now could be changed for the value omega multiplied it by gradient z. Again, I mentioned, if you take the gradient z, you actually have a unit vector in direction of z. Then here there is the of angular velocity, and this is exactly what is it. It's actually the same. So just to stress that I wrote it here. So, and then we just have to multiply that stuff on the radial vector in spherical coordinate system. As already I showed to you that it has very simple representation, x, y on y and z, grad z. Okay, this is just again to stress that all this stuff is exactly equal to the radius vector. All this stuff. So now we just multiply with the cross product vector multiplier all this stuff. In using right screwed rule, we can express all these values very simply. Of course, one of them is absent, because if we multiply this with this, we will have a 0, and only two terms remains. Let's write them down. And this first term is, then we are, of course, can remove like that, and so eventually we have x grad y and minus y grad x, using all this identical notification. And so you see that it has actually only two components, in y and x direction. So it's sort of the plane flow, very plain. Thus it's actually, there is a solid body rotation. So, and in fact, this flow becomes, because it's such a flow, to then we can express it in coordinate system, not only like this formal representation. We can use another representation which is rather openly used. So we have x coefficient is minus y, x coefficient is just x, And of course, the z coefficient is coordinate is 0. So just I'll show here. This is gradient x. This is gradient y. And this is gradient z. Something like that. Just to memorize how it's works. So after this expansion we have made, this expansion, we can use this more simplified stuff and install it in the equation 14, which is expanded like that. And eventually we have very long expression. Maybe I'll write it down without glasses because it's difficult to see one. So if we substitute this to this and open all the brackets, at least not all, but then group somehow, then we have such a lengthy stuff. Hopefully I'll fit it here. So of course we start from the x part of the partial derivatives of x. Then we have combine all the stuff which in these brackets with consequences multiplier. So it's let's use Cartesian coordinate because it's easier. So first we wrote down the first two terms which are coming actually from here. There is only two terms which is responsible for solid body rotation. Then we have Reynolds term which is corresponding to the u grad u coefficient. U will be appear later, but now we have u grad, just u grad. And here the next is egret. It's interesting when we consider this Reynolds term, we have some symmetry. X component working with X gradient and Y complement with Y gradient, and of course Z component is certainly working with Z component. So there is some sort of rule. Okay, I'll keep square brackets just to remind that it's come from here. And it's everything of this, it is acting on this value, which is this term can be written like that. So then we have viscosity term. It's transformed very easily because actually while there is a solid body rotation, so it just cancelled, and we remain with very simple stuff like that. And let's express in this way. Of course, we divided everything in initial Navier-Stokes equation by rho, which we made in the formula 12. It's in the previous place. And we have X component of the general force And also we have partial derivatives of thermodynamic pressure on X. And that's all. And this is the one component which is in direction of X. Then we consider another component in direction of Y. Of course, all the things are playing the same game. It's interesting that here we directly quite directly we replace this. So maybe I even will not write it down just to show that it's exactly the same. But this one is a bit different. No, it's also exactly the same. Okay, it's also exactly the same. It's interesting that about exactly the same. Oh no, it seems mistaken the notation. I see. This is the same, but this one. Oh, sorry, it was in notation some example, so I'll have to correct. So here. Oh no, it's correct. Yeah, I thought that it's not correct, but it's correct. Yeah, sorry, because it's acting in another way. So I just can repeat that. But here there is some changes. So we have omega x plus v y is equal nu over gradient which is acting on y and plus the same value like here, but here we have y component. And if we consider Vz component, sorry. Actually, we have the same. And here there is some difference. And it's quite simple, just Vz, because there is no another component in the direction of the rotation. And eventually we have this with z. Okay. So we write down all this lengthy formula. And this equation after elementary transformation takes the form. So if we make some elementary transformation, just multiply everything using right screw draw rule. So after this eventually transformation, we arrived to the following system. This is okay, maybe Хорошо. Okay. Okay. I don't know if it is here or not, but I will try. Then we again have the same things. Just to make I will write down them dvx by dt minus omega x minus omega y dvx by dy plus omega x dvx by dy minus omega vy. Then plus we can write it on the vector field like that. X and of course these terms remain the same, like from here. Okay, but nevertheless I will write it down. And the similar terms appear in other coordinate. Yes. And again we get this Reynolds stress, but against the y velocity. And here also we have against y velocity viscosity term, and finally pressure term. And the final, there seems space for the final equation of all this stuff. Oh, sorry. All the signs usually connected with some lengthy formula, which you should write down. And unfortunately, often you make some mistake, but you should be careful to avoid any mistake. Hopefully I did so. But it was written before. And then plus omega x. Again, dv z. Z is the last component of the y. Then we again have this term. There is no rotational term here, but still this term of course remains. Okay, let's put it here because maybe just stress that there is no rotational term. We put 0 here. But this of course remains. As well as the viscous term. Okay, seems I manage. And here we have, of course, some terms which has a common multiplier, and so of course we collect all these terms against the different common multipliers, and eventually we arrived on the, okay, should remove some stuff. Now we don't need that. We remove. And even that is not necessary. Remove that as well. Okay, we keep only that. And after identical transformation and collection different members of this three equation against the same multiplier, we simplify it a lot, and eventually we arrived already to the same equation as we stated before, but nevertheless still in some expanded form. Let's write it down here. There is dv vector by dt. Of course, we collect this from this, and this, and we just take dv by dt. Then we can find the part which corresponds to the square of the angular velocity. And this corresponds to the next term, omega squared by 2 gradient. We can write it like that. This is a gradient in the x-y plane, which corresponds to the centrifugal force. Then we have Coriolis term, which appear like that. First of all, dv by dx plus omega x dv by dx And then eventually we have this omega, which is directed in the z direction with my lovely gradients, that stuff. Maybe we even put it in brackets, multiplied it by velocity. And then we have this Reynolds term plus up to V. And also we have viscous term in vector form. And also there is, of course, pressure and force term, which is just multiplied by. Okay, so we just shrink a little bit. Let us make the final transition to the rotating coordinate system. So let's make the final transition to the rotating coordinate system. And so this rotating coordinate system we denote by the special symbol. This rotating coordinate system So we just use this coordinate because rotating coordinate system has only working in the x and y direction. So rotating coordinate system is literally has a different x and y coordinate, but the same z coordinate. So we can write it down like that. And here the index omega means that the coordinate system rotates at a constant speed, omega equals constant. So here we use this stuff that the omega equals constant. The absence of the index omega for the vertical component z correspond to the fact that neither this coordinate nor the corresponding derivatives require transformation. So it's not required transformation, so there is the same coordinate system. The remaining coordinates and derivatives must be transformed. To perform the transformation, we will use the fact that the transition from the initial coordinate system to non-initial coordinate system rotating in the azimuthal, for example, like in this figure, we can rotate it in azimuthal direction. Phi is described by the formula. So actually we can describe this rotation by the simple formula because it's under rotation. So we, okay, I forget to put number here, 118. Described by the simple harmonic formula. So we have x omega equal angular rotational rate in the coordinate rate for the particular point of the rotating coordinate system, cosine omega t via here and x plus sine omega t y And this is for x coordinate related to the real coordinate. And this is for rotating system, y omega equal minus n omega t x plus cosine omega t y. So that's 119 formula. Okay, and formula 19 follow from the geometry of transformation and from the fact that at the initial moment t equals naught, both coordinate system completely coincides. And using 19 in the 18 in this equation, the velocity is function. We find that the velocity is function like next I will write down that the velocity itself is equal velocity in rotating coordinate system which depend on t actually x in rotating coordinate system, y in rotating coordinate system, and the z which is the same in rotating and non-rotating coordinate system. It's always the same. And so we can expand it in terms of the two variable, because actually we know that there is a two variable which substitute variation for this system. Omega x component. This is in rotating coordinate system. X component is actually related to the velocity itself. That it's x component in the rotational system. And then we multiplied it by unit vector again in rotational coordinate system. And it's now depend on time, x and y, and of course independent on z. And the same situation is for another component. Another component is v omega y gradient y omega t x y. And the final thing is quite simple because it's related without any transformation just directly to z component, which is the same rotating, non-rotating. So this is looking like that. So it's formula 120. So after that, and it is necessary to take into account the time dependence both for rotating coordinate and for unit vector. Accordingly, we obtain semi-final formula, also a bit lengthy, but okay, I'll remove that and here try to. Okay, so we we account the time dependence for both for rotation coordinate and for unit vector, and accordingly from this all these three previous formula, actually mainly from the, well, not all the three, we are getting the semi-final system, not final but semi-final, which we put partly in rotating and non-rotating system. So it's look like that, dv by dt is equal dv rotating by dt is equal dv rotating by dx rotating. Oh, sorry. So here we expand this Reynolds stress term, okay, in similar matter. So this Reynolds stress term, there is only two of them because some is removed, and then okay, plus x. Okay. We also have some transformation of the unit vector. It's interesting to note of the, against this rotational coordinate system. We also should take it into account, and another unit vector. And this all is actually equal. Mm-hmm. Equal. Oh, seems I missed something. Sorry. Okay, we stop here. 2 x equal. Okay. dv. Sorry, I mistaken it with another one. So now I put in it correct. So we expand on the Coriolis term and other term. I keep all the intermediate steps. Of course, maybe I choose maybe to prolongated way. If somebody suggests more simple way, I will be very happy. So this is the result of substitution of this stuff to this initial equation. And then we have this, okay, not so many remain. Sin omega t plus y cosine omega t. Okay, square bracket break. So we have this Coriolis component of the velocity in direction of x multiply. Then we have this dv omega dv omega omega. Yeah, and not so much remain. Plus this is x component now. And it now unit vector in x direction and another unit vector in y direction. Plus. Okay, and we finished up with the y component of rotating velocity. Again, the same stuff, similar stuff. Again, of course, we have all this Coriolis term, which are expressed only in one plane, which is related to x and y coordinate. And final thing which can be wrote down here. Over dt plus omega here I forget the vector mark. Okay. Omega x omega 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 plus Okay, we can put point here. It's formula 121. If you follow all the derivational step, you will see that it's not complete equation 19, but only the part which related to this Reynolds stress term and rotational term. Because if we consider this part which is responsible for the additional for the viscosity and for pressure and the applied different forces, it's not here because it's working in the same way. So now starting again from 19 and from the rules for differentiation in complex function, we obtain for the first and second derivatives, we need further. So we further need this relation for the next second and third derivatives. Okay, we can leave only 19 equation because it's okay here. This can be removed. So we can transform these derivatives like that. So first we start from the x derivative, which becomes from this actually formula 19. This x derivatives becomes cosine omega t d by dx omega minus sine. We obtain everything like that, directly differentiation this expression, corresponding expression. Then we have for the y the similar stuff, for derivatives on y. And the same derivatives, but here sine and here the cosine. And the final derivatives in all this system, it's not so lengthy. So finally we can also approximate the some Laplacian stuff, which is in the rotating coordinate system, take the form which is will be used in actually in the place where the viscosity comes. This stuff is coming from this relation. So we relate the Laplacian term in non-rotating system with rotating one, and it's exactly the same. It's possible to check. Okay. So all this is formula 122. All these three. I just outline it like that. Okay. You can make a picture. So from this, after identical transformation, we conclude that the nonlinear initial term and all the relation on the right-hand side of 18, which I showed you previously, now it's removed, containing derivatives of x and y are exactly compensated by the similar term of 21. 21, which is here, this 21, which represents the corresponding term which is responsible for the v grad v or v grad v and partial derivatives of the velocity. So it's sort of the Euler part. And finally, substituting the relation 23. Okay, so we allowed it to the relation 23, which if you manage to, please maybe you take the shoot over. Oh, maybe I remove from here. I will keep that. That you will see. And I remove that. Because it's too intermediate one. And after actually all this identical transformation, after this lengthy derivation, sorry for that, we have okay. So eventually we have this relation that minus v grad v plus, now we replace the viscosity term to the place where velocity is. Then we should add this pressure term and equal minus So we have relation in rotation and non-rotational term. So it's 123. And the other two terms on the left-hand side of the previous equation 18, containing derivatives of x and y, are exactly compensated by similar terms in 21. 21 I still, okay, it just was removed. And after transformation on 19 and 22 to the rotating coordinate system, finally substituting this final relation, which we got in relating of coordinate system, different coordinate system, we obtain 14 and 15, which was required for the proof. I guess now I will find the 14 and 16, which is okay. Okay, this one, 14 and 16. 14 and 15, sorry. 14 and 15. And so this actually we when put and make the identical transformation, we arrive to this system from 14 and 6 and 15, which is actually the final system. Sorry for such a lengthy derivation. Of course, I will be glad if you suggest more simple one. Maybe you can succeed to suggest more simple one, so it will be quite good. But the goal is to arrive from the initial system to the rotating system. Maybe I chose not so direct and not so pleasant way. I will be happy if you find more simple way. Okay, so maybe we'll have a break. Yeah, maybe it's